Good enough. What I did in the lab is I kept adding copper into the beaker until I got a mass of about 63.546 grams. That number, I want you to notice, is the same number as the atomic mass of copper on the periodic table. So you go to the periodic table, here's copper. We can see it's element 29, and underneath it has an atomic mass of 63.546. And that's the mass in atomic mass units on average for a single copper atom. So what is a mole? A mole is that number, 6.022 times 10 to the 23rd power. If I were to add that many copper atoms to the beaker, that's the number of copper atoms it takes to get the same mass in grams as that number on the periodic table. This works for any element on the periodic table. Let's look at this number a little more closely. The nickname for Avogadro's number, or a mole, is the chemist's dozen. Just like a baker's dozen is 13, and because bakers often work in that number, a chemist's dozen is a mole because we often work in that number. We like the mole because by working with this number, that allows us to use the periodic table for those masses in grams. But what is that number? It's a gigantic number. We are in the sextillions in terms of how many digits out we are. Just for a sense of scale, at the time of this filming, the population on Earth is around 8 to 8.5 billion. But we're like more than half of a septillion in terms of the number of things in a mole. So in this beaker with about 63.55 grams, I have about that many copper atoms in there, 1 mole of copper atoms. And that weight, that mass, is the same as a number from the periodic table. So in chemistry, we're usually going to be talking about things like atoms, ions, molecules, formula units for ionic compounds, but technically speaking, it's just a number, which means we could be talking about donuts, Joshy Washies like me, really anything. I want to show you an approach I use to talk about like why Avogadro's number is so special and so powerful, and why it's not just some random number. Where does it come from in a very practical sense? We're going to try to make this gigantic number of 6.022 times 10 to the 23rd power a practical number in your mind. So we have a big goal in front of us. So I'm going to do this by talking about masses. If we were to try to weigh out one carbon atom, get its mass, we would, or if we were to try to calculate it, we would have 1 for that one carbon atom, and we would multiply its mass, or that number, by its mass of 12.01 AMUs straight from the periodic table. There we go, there's carbon. If we were to convert that into grams, we would take the same calculation of 1 times 12.01 AMUs. We would multiply it by the conversion factor between grams and AMUs. That's 1.6605 times 10 to the minus 24. And we would get this number, about 2 times 10 to the negative 23rd grams. All right. My focus in this video isn't for you to get too lost into this math, as interesting as it is. I want you to just notice that if we were to calculate this mass, we have a decimal point and a lot of zeros, and then some number, and that's grams. So this is what I want you to pay attention to. In order to get something, decently detectable on some, average lab scale, we need weights or masses to be approaching, 3 decimal places out, at the very least. And to get like a more decent measurement, maybe we should just be 1 or 2 decimal places out. But we're nowhere close to that. So you think, let's just get more carbon atoms. Sure, let's get 1 million carbon atoms. Maybe 1 million will work. That's enough carbon atoms, right? So, and 1 million's 10 to the 6th power. So to get the mass in AMU, we would go 10 to the 6th power times 12.01 atomic mass units. And to calculate that in grams, let me show the calculation right here. We would go 10 to the 6 times 12.01 AMUs times 1.6605 times 10 to the minus 24 grams per AMU. All right, so let's do this calculation, or I guess you can watch me do the calculation. So does a million carbon atoms give us enough material to get a measurement? Let's write out that number. 1.994 times 10 to the minus 17. Writing it out, we get this number. Again, to be detectable on the balance, we need to be here, and we are not there. So let's cut to the chase. In order to get something that could be measured, and possibly as a bonus, an easy number to work with, let's see what happens if we were to have this many carbon atoms. Let's use that Avogadro's number. 6.022 times 10 to the 23 carbon atoms. So, to calculate that mass in atomic mass units, we would go 6.022 times 10 to the 23 and multiply it by the mass of one carbon atom, 12.01 AMUs. If we were to calculate that in grams, we would take that same statement. And one thing that helps me remember Avogadro's number is that it has a 22 and then a 23. And then the conversion factor, 1.6605 times 10 to the minus 24 grams per AMU. All right, I invite you to try this calculation on your own. For me, this is one of the most magical moments possible in chemistry. I'll do it too. And to 4 sig figs, that would be 12.01 grams of carbon. So, if you measure out this many carbon atoms, that mass will be equal to 12.01 grams, which is exactly the mass from the periodic table. So that is really special. So Avogadro's number gives us that superpower. So what just happened? Well, again, we went to the periodic table and we noticed if we measure out an Avogadro's number of things, a mole, we're able to use the mass, but think of it in grams instead of in atomic mass units, all right? So I'm going to argue that using this knowledge, we can now use something called a molar mass. And a molar mass will have units of grams per mole. Up until this point, we were thinking of those tiny atomic mass units in terms of the mass of an atom, and we would have the units of AMUs per atom, AMU over atoms. So what we did was we actually did some conversion factors in the process. So one atomic mass unit is this is 1.6605 times 10 to the minus 24 grams. We have canceled out our atomic mass units. We now have grams at the top, and there are 6.022 times 10 to the 23 atoms in 1 mole. And now we have atoms crossing out, and the only units we're left with are grams over mole. So another way of thinking about Avogadro's number, I think this is really cool, especially for anyone that enjoys mathematics. Avogadro's number is simply the number that is making sure I'm getting my terminology right here, a multiplicative inverse, also known as a reciprocal, of the gram to AMU conversion. Avogadro's number is simply the number that takes this conversion and turns it into a 1, all right, and leaving us with grams over mole instead. So now going forward in this course, we're going to work in molar masses in grams per mole from the periodic table instead of those annoying AMUs over atoms. I thought I would close this video with some example molar mass calculations. Let's start with water. This is really common in any chemistry course. So get out a periodic table and look for some molar masses. All right. Now this periodic table I've become really attached to ptable.com. I like it for many reasons. However, I would say for Chem 101 course, it's probably not necessary to have molar masses that go to the beyond the 100th place. Like I've seen periodic tables where hydrogen will just be 1.01. And I think for Chem 101, that's usually going to be good enough. But we'll just stick with this periodic table today. So we have 1.008 for hydrogen. And then for oxygen, we have 15.999. Maybe yours says 16.00. If you have the one that says 16.00, please write those 00. Someone measured it, so you gotta respect the sig figs there. All right, so to keep track, we have 2 hydrogens and we have 1 oxygen. 2 times 1.008 grams per mole for the hydrogen contribution, and for the oxygen contribution, 1 times 15.999 grams per mole. That will give us subtotals of 2.016 and 15.999. So to get the molar mass for a compound, you just add up the subtotals from each element, and this is going to end up (18.015 grams per mole. Perhaps you got 18.02 if you had a periodic table with less sig figs. But there's that. Get used to something in the ballpark of 18 in a chemistry course working with water. That's going to happen all the time. Carbon dioxide, another common substance. 1 carbon, 2 oxygens. Carbon, 12.01, or this periodic table has 1. Starting to run out of room a little bit here. All right, here we'll just kind of go over here. Sorry, a little bit sloppy today. 12.011, and then we're going to have 31.998. Let's go ahead and add those up. My brain calculator is not working so great anymore, so I'm going to move on over. All right, and we get 44.009 grams per mole. Okay, sodium chloride, hopefully you get 58.44 grams per mole. 1 sodium and 1 chlorine. Or if you're using my periodic table, or I should say ptable.com, 22.990 plus 35. Oh, same answer. Sweet. 58.44. Let's do this last one together. This is a hydrate. Okay, this is potassium aluminum sulfate dodecahydrate, also known as alum, used in water purification, antiperspirant deodorants, and even cooking sometimes as an acid source. All right, so let's do alum together. We have 1 potassium, 1 aluminum. All right, and now we have a polyatomic ion in parentheses. So if you get lost in like how to think of these chemical formulas, it can definitely be helpful to come up with a drawing. We have 1 potassium, we have 1 aluminum, we have 2 sulfates, 2 of this whole thing in parentheses. So there's sulfate number 1. And here's sulfate number 2. You don't have to draw perfectly, technically correct Lewis structures to do these problems. And then we're going to have 12 water molecules. All right, I'll pause the video so you don't have to watch every single one of these. All right, there we go. So 1 potassium, 1 aluminum. We have 2 sulfates, and then we have 12 waters. Now what you could do, what I don't do, but what you could do is count all the oxygens in total here, and all the hydrogens in total, and all the sulfurs in total. For me, I think it is easier to treat the waters separately. You could even treat the sulfates separately if you wanted to, but I can clearly see I have 2 sulfurs. And ignoring the oxygens in the waters, we have 1, 2, 3, 4, 5, 6, 7, 8. And then I'll treat the waters entirely separately. All right. So that's how I prefer to set up my math on hydrates. Treat the waters separately. All right, let's fish for those molar masses. 39.098. Aluminum, 26.982. Sulfur, 32.06. And we have 2 of them. Oxygen, that one I remember, 15.999. And then water we already previously calculated, and that was 18.015. All right, let's get all of these subtotals. I can do that one in my head. And that one. That one I can do in my head. 64.12. And our sig figs would end there. Well, actually, no, we went one over. Depending on what class you're in, you know what? We'll just stick with the 101 sig fig rules and go like that. All right, let's sum them up. Not going to matter anyways because we don't have sig figs in the thousandths place for the sulfur. 39.098 plus 26.982. And unless you're taking an exam, it's definitely good to double check these on a reliable source on the internet. The Wikipedia ones are usually good, so long as if you look up the correct hydration state. But if I'm doing like, a research report or, original research, I'm going to go to NIST for the most accurate, precise, and authoritative molar masses. Anywho, let's get the answer, huh? 474.37 grams per mole for alum. All right, so you just use the periodic table and sum them up. All right, I hope this helped for you getting a sense of what a mole is. So happy mole day. I guess that was yesterday. But yeah, if I owned a restaurant in this world, I would make mole day one of those days where there'd be like a guacamole giveaway or promotion or something like that. There we go, guacamole. Happy mole day. I think mole in Spanish means like a sauce or something like that. I didn't look that up before this video. Oh well, it's recorded now. And the mole, the number for a mole is Avogadro's number. So you can read up on Avogadro's number, named in his honor because he did a lot of work involving mole relationships when he was studying the chemical physics of gases. So Avogadro sounds kind of like avocado, so it adds onto all the sort of guacamole sort of puns and stuff. But anywho, hope this video helped, and any questions, comments, or requests, just let me know. I hope you have a great day. Take care.